Hi everyone, welcome to this class 16A, where Wout Sijsouw and myself, Jeroen Koelemij, will tell you more about thermodynamic energies and about something that's called fundamental thermodynamic relations. And in order to do so, we will actually make use of some of the math that we learned about during class 15A and class 15B. Now, earlier on, we indicated that this series of lectures, classes 15 through 17, were aimed at developing mathematical tools that we can use to, on the one hand, get a better understanding of these curves we encountered in the thermodynamic diagrams. And of course, these curves are nothing but relations between thermodynamic properties like T and S. And we would like to understand the behavior of these curves a bit better, at least beyond reading off just values in tables or diagrams. And we've also seen that some thermodynamic properties, for example, entropy, are not so easy to measure. And it would be nice to have some mathematical tools that would allow us to translate measurements of easily measured properties like pressure or temperature into things like entropy. So one of the mathematical tools that we needed to learn about were partial derivatives, and I would like to review those again quickly, and this time in a slightly different way. So let's assume we have again a function z, which is a function of independent variables x and y. Then we can write the total differential in terms of these partial derivatives. And we learned that to evaluate this first term, well, we could take the derivative of z with respect to x, assuming that the variable y was held constant. That's the same as saying that dy is 0. And if we plug in dy equals 0 in this expression here, we end up with this expression, this equation. Now we can divide both sides of the equation by dx, and then we find this expression, which essentially says that we can evaluate this partial derivative by just taking the normal derivative of z with respect to x, but keeping in mind that we treat the other variable, y, as a constant. So we learned about partial derivatives, we learned about total differentials, we learned about non-total or inexact differentials, which are denoted as delta z. We've also learned a trick that allows us to use this expression, this total differential, to describe changes of thermodynamic properties under the assumption of small changes of state variables, so small values of delta x and delta y leading to a small value of delta z. But we also learned that in the case that the changes are much larger than that, it's actually better to perform the path integral, which is expressed over here. And we also learned that state functions and path functions behave quite differently under path integration. For example, path functions have a path integral that gives a value that's very dependent on the path that you follow during the integration. Whereas for a state function, the outcome of the integral is always the same, independent of the path that you took. Now in this class 16A, we will take a look at the different thermodynamic energies that are around, and two of them we have already encountered, the internal energy and the enthalpy. Today we will add the Helmholtz energy and the Gibbs energy to that. And we will also see how these functions, as they are shown here, how they actually represent fundamental thermodynamic relations. And what I mean by that is that they are relations, or they provide relations from which we can derive all four thermodynamic state variables, even if we only know two of them. And this is just a different way of explaining the state postulate that we have seen before. But now, today, we will see how that's actually derived mathematically. So let's start with a quick recap of the energies, the energy forms that we had seen before. The internal energy is the energy of a substance due to the motion of the molecules that make up the substance. And it's not just the motion, the velocities of the molecules, but the molecules themselves may also be vibrating or rotating, and that also represents energy. And all these things together sum up to the internal energy of the substance. We like to express the internal energy by the variable U, and we make it a function of the independent state variables entropy and specific volume, and then we can write down this specific total differential. Now, if we look at the form of this equation here, and if we combine that with the first Gibbs equation, and remember that this first Gibbs equation we can derive quite easily from the first law of thermodynamics in combination with the second law of thermodynamics, then we see that this partial derivative here equals T, and this partial derivative here equals minus P. And actually that allows us to define temperature and pressure in terms of the partial derivatives of the internal energy U. So we had this function, U of S and V. Now let's take a look at how this function behaves in the US plane. So we have this partial derivative that we just defined to be equal to the temperature. Now we know that if the temperature goes to 0, then also entropy goes to 0. When the temperature goes to 0, this particular partial derivative, also becomes 0, which means that if entropy goes to 0, the slope of the curve, which is represented by this partial derivative, also becomes 0, as shown by this red tangent here. And the intuitive interpretation of what's going on is the following. When the temperature of a substance becomes 0, then the molecules that make up the substance, they just stop moving. Everything freezes out. And there's nothing you can do to reduce the temperature even further. There's no further decrease or change of the internal energy possible, and that's reflected by this partial derivative becoming 0. We also know that the temperature is always larger than 0, and because of that, this partial derivative is always positive, and that implies that U, as a function of S, is monotonically increasing. And another thing we can derive, if we take the first law of thermodynamics and combine it with the Clausius equation, we can show that if you increase T, then this function U increases as well. So what does that mean? Well, if this curve here is for a specific temperature, remember temperature is fixed here. If we would plot the same curve but for a higher temperature, then the curve would be higher up here as well. Now, likewise, we had seen that the partial derivative with respect to a specific volume equals minus the pressure. So this is again the function U, but now plotted in the UV plane. Now, if the specific volume goes to infinity, we know that the pressure of the substance goes to 0. And if the pressure goes to 0, this derivative goes to 0 as well. And that's indicated here by this red tangent, which is valid for infinitely large volume. Now, we also know that the pressure is always larger than 0, so minus P is always smaller than 0, so the slope is negative, and in fact, U, as a function of V, is a monotonically decreasing function. We also see from the behavior of U that the steepness of the slope gets smaller and smaller as V becomes larger. And the steepness of the slope, and I'm talking about the absolute value here, that's basically the same as the pressure, which means that because this curve is getting less and less steep, the pressure goes down and down. So with increasing volume, pressure goes up. We already knew this, of course, for a long time, but this is basically deriving it from the functional behavior of this function u. So we are inverting our reasoning. Now, so much for the internal energy. We've also come across enthalpy, which is a combination of internal energy and the flow work, PV. Now, we like to write enthalpy as a function of entropy and pressure, and that allows us to write down the following total differential. And we will very soon see why we choose S and P here as variables and not S and T, for example. Now, if we combine the first Gibbs equation with the definition of enthalpy, we find that the total differential dH is equal to TdS plus VdP. And you may pause the video to see if you follow this derivation here. And this expression here is also called the second Gibbs equation. And now you will notice that if you compare this guy with this one here, that we find that this partial derivative equals T and this partial derivative equals the specific volume. Okay, this is interesting now because we saw that from the internal energy we can write definitions for the temperature and the pressure in terms of partial derivatives. And from the enthalpy we could do a similar thing, and we again find temperature and specific volume. Now, if we look at these four expressions, it's very dissatisfying. It's not symmetrical at all. So why does T appear here twice and P only once and V as well? I mean, T has no special status in thermodynamics compared to pressure or specific volume. So why is this happening? Or might this just be a hint that there are more energies like the enthalpy, and internal energy, but different ones? And well, indeed, there are two additional energies which can be obtained from the internal energy itself and the enthalpy itself by subtracting the term Ts. And these are the Helmholtz free energy and the Gibbs free energy. And the word free here means available because they represent the energy that can be converted into useful work from a thermodynamic system. And it's important to keep in mind that for the Helmholtz free energy, it is assumed that we're looking at processes that take place under constant volume and constant temperature. And likewise, for the Gibbs free energy, the assumption is that we're looking at processes that take place under constant pressure and constant temperature. Now, in equilibrium, these free energies, they have the property that they will go to a minimum value when equilibrium is reached, whereas entropy tends to go to a maximum value. So any spontaneous process in thermodynamics will lead to an increase in entropy. We've seen that before. And at the same time, it will lead to a decrease in the free energy. So like entropy, free energies indicate the direction in which a spontaneous process will proceed. And this is a concept that is used often in chemistry. Now, in the following movie, Wout will show you a few interesting properties of the Gibbs energy. So have fun.
This video is about Gibbs free energy. And Gibbs free energy, like Helmholtz, is a specific type of energy which you can take into account. And Gibbs free energy is the amount of work that can be obtained from a process in which no expansion takes place. And in this Gibbs free energy, we assume that the pressure is constant and the temperature is constant. of course, as we always talking about quasi-equilibrium, it means it's constant in this quasi-equilibrium state. So actually there might be slight changes, but very, very small. And well, the Gibbs free energy can of course be written into an equation, and this equation looks like this. The Gibbs free energy, G, is equal to H enthalpy minus temperature multiplied by the entropy, and that is equal to, if we write out what enthalpy means, is equal to U plus pressure times the volume minus Ts. So this is the equation for the Gibbs free energy. And well, unlike the Helmholtz free energy, in the Gibbs free energy the pressure is assumed constant, and the Helmholtz free energy volume is assumed constant. So the Gibbs free energy, as you can see over here, is a function. Actually, it's a state function determined by the pressure and temperature. And this Gibbs free energy is especially interesting when processes change. For instance, in chemical processes, you might think, well, I'm a mechanical engineer, so no interest in chemical processes. Well, I think especially thermodynamics, but material science as well, is really close to chemical engineering. And if you become an engineer in, for instance, a chemical plant, you really should know about this. And the beauty of this is that a lot of mathematics is involved in understanding the Gibbs free energy. So what is the relevance of the Gibbs free energy? Well, when the Gibbs free energy is minimal, a system will be is in equilibrium with its environment. So when G is minimal, the system is in equilibrium with its environment. And this is really interesting because we know from this we can derive that if G is decreasing, so let's assume that if dG, the derivative of the Gibbs free energy, is increasing, so decreasing, so smaller than 0, then we know that the system tends to become in equilibrium. So dG decreases, the amount of free energy decreases. And we know that this will be the direction in which a process occurs. So that's really interesting because we can use this. We can use this to predict what will happen when we have a certain process. And of course, there's one thing. Of course, the entropy, ds, the difference in entropy should be larger than 0 or at least equal to 0. Then we'll have a spontaneous process. Because of course during a process at least entropy should remain constant, or but in reality it will always increase, otherwise we would have a reversible process. So that's a boundary condition. So since this is very this dg should be smaller than 0, it's actually very useful. So we can predict what will happen in a process. And actually this is really important for even phase changes. So I'm going to explain you mathematically schematically, how this determines phase changes. And for this, we will first need the derivative of the Gibbs free energy. And for the derivative of the Gibbs free energy, I need to take the derivative of dg. And I'm going to derive it over here. I have to take the derivative what is written here. So dg is equal to the derivative of h minus ts. Well, and over here I've already written down h and dh, because dh is over here, and in dh du is incorporated and du is written here. So let me write this is equal to so first dh is equal to du plus dv. So dh is equal to t ds, so it's over here, minus p dv plus p dv plus v dp. So this one drops out, that one drops out. So now I can write them down over here. So it's equal to t ds plus v dp minus t ds minus s dt. So this one drops out, that one drops out. This is equal to dg is equal to v dp minus s dt. To make it a little more mathematical, I'm going to write down the partial derivative. So the v, from this it follows that v is equal to delta of d dg dp for a fixed temperature, and over here the minus entropy is equal to partial derivative of g with respect to T for a fixed pressure. Okay, so now we've got the partial derivatives of the Gibbs free energy with respect to pressure and temperature. Well, and of course, the best way to get a feeling for this is to write everything down into a graph. So I'm going to make two graphs, one for a constant temperature and one for a constant pressure. So over here the pressure is constant, and we've got the temperature on the horizontal axis, Gibbs free energy on the vertical axis, and here I've got the temperature constant, and over here I've got the Gibbs free energy and the pressure. To give my diagram any meaning, I'm going to use this equation. The volume is equal to the d Gibbs divided by d pressure, and I'm allowed to do this since pressure is assumed constant for now, temperature is assumed constant for now, so I don't need my partial derivative anymore. This will drop out. So for this, in this case, I can just assume temperature is 0 and these are d's and actually not the partial derivatives anymore. Okay, well, so I know this is the volume will be the slope of the derivative of the Gibbs energy with respect to pressure. And actually I know if the pressure is really, really low, I can assume that my volume is very high. So the rate of change of the dg to dp for a very low pressure will be very high. Well, and I have to take a look at my Gibbs free energy as well, and I see that that a constant is involved, and in this case it's internal energy. So from somewhere over here, I will have a very steep increase of Gibbs free energy, and it will slightly decrease. And at a very high pressure, of course, my gas will be very compressed, so the volume will be very small, so the rate of change will be very low. So in the end it will convert to a constant value. And this is for a gas. So in the gas phase. So after that, of course, I'm going to consider a liquid. And of course, we know that if you compress a liquid, that's very hard compared to a gas. So for a very high pressure, the volume will be slightly lower than for a very low pressure. So this will look more or less like this. So here we've got a liquid, which is harder to compress. And of course, when we've got a solid, that's even harder to compress. That line would be almost horizontal. So this might even be too steep. So solid. So here we've got an idea of the behavior of the Gibbs free energy with respect to pressure for a fixed temperature. So now let's have a look at the Gibbs energy with respect to temperature for a fixed pressure. So from this equation, we can derive from this that the rate of change of Gibbs free energy with respect to temperature will be equal to minus the entropy. So for a gas, when we have a very low temperature, we know that the entropy will be very low as well. Not a lot of movement. And as temperature increases, we know that entropy will increase as well. But since there's a minus, it will have a negative slope, and it will look like use the same color, look like this. So this is a gas. So for a liquid, this will be slightly, the entropy will be slightly lower, so less chaos, to put it simply. So this the rate of change is slightly it's less steep, so it will look like this. So here we've got the liquid. And if we have a solid, the entropy is even lower, so the rate of change is even lower. So that will look like this, a solid. When the Gibbs free energy is minimal, the system is in equilibrium with its environment. So, and let's have a look from here. In this region between here and here, we can see that the Gibbs free energy is minimal for a gas. So from here to here, the Gibbs free energy is minimal. Minimal Gibbs free energy. So in this region of temperature, my material, my substance will be in a gas phase. Well, if we increase pressure, then my substance wants to be in this region. So when we increase pressure, my Gibbs free energy is minimal here, so it wants to be a liquid. And if we increase pressure even more, the lowest amount of Gibbs free energy is for a solid, so my substance will become a solid. So over here and over here we've got the minimal Gibbs free energy. Well, something similar will happen for constant pressure. So if I increase my temperature, first the lowest amount of Gibbs free energy is for a solid. So when increasing temperature, it will become a liquid. From there it will become a gas, and then it will remain a gas for the rest of the time. So over here, there and there, we've got the minimal Gibbs free energy. So I hope this video gave you some insight into Gibbs free energy and why it is useful to use the Gibbs free energy. Good luck with the assignments and the rest of the lecture. Thank you very much.
So apart from the Gibbs energy, there's also the Helmholtz energy. Like we said before, it's the amount of useful work that can be obtained from a closed thermodynamic system, assuming that it is at constant temperature and constant volume. For example, you can think about a closed reaction chamber in which a explosion takes place, the combustion of a gas, for example. So the Helmholtz energy is written in the following form, and let's now write this Helmholtz energy A as a function of temperature and volume. Then we can write down the total differential as follows. We have seen that many times before. And now we can take the first Gibbs equation and combine it with the definition of the Helmholtz energy. Then this can be combined to find a third Gibbs equation. And you can stop the movie if you like to see if you can follow this derivation. And what we find is that dA, which is also expressed here, can be written in this form, and that immediately leads to the following two identifications. This partial derivative here is minus the entropy, and this partial derivative, this guy, equals minus the pressure. Now, as we saw earlier on, we had these four partial derivatives that we derived from the internal energy and from enthalpy, and that led to this dissatisfying situation where we had two partial derivatives being equal to t, and only one to p and only one to v. Now, in the movie by Wout and in the previous slide, we saw that we can also take partial derivatives of the Gibbs energy and the Helmholtz energy, and that gave us four additional partial derivatives, and in fact it gave us twice the entropy and once the specific volume and once the pressure, and now everything is nicely symmetric again. Great, yay. It's also interesting to look at this function u, which we chose to be dependent on the entropy and specific volume. And what's interesting about it is that, well, assume that you know this function u. Then if you know the value of s and v, you also know these partial derivatives, and you know the temperature and the pressure. So that's sort of a mathematical demonstration of the state postulate. You know two thermodynamic variables, and you can find the other ones. And the same goes for the enthalpy, provided that we write the enthalpy as a function of S and P. So this explains also why we chose this particular combination of variables. So also here, you know the entropy and the pressure, then you can derive T and V, provided you also know H. It gets really interesting if we look at the Gibbs energy. So assume we know the function of the Gibbs energy, and if we know the pressure and the temperature, which are quantities that are easily measured, then we can derive the entropy and the specific volume. And a similar thing we can say about the Helmholtz free energy. So this is what is called a fundamental relation. You see here 4 fundamental relations that we use to convert any pair of thermodynamic properties into the values of other thermodynamic properties. Just a little note on the naming of things. These thermodynamic energies, U, H, G, and A, they're also called thermodynamic potentials. And there is, in fact, an analogy with electrical potential or voltage, of which we know that we can always define a reference voltage that we can subtract. And what does that mean in the context of these thermodynamic energies? Well, for example, if we evaluate the Gibbs free energy, we're not going to evaluate the total free energy of the universe, but we're starting from a reference value that applies to our system in the lab. So we choose actually a convenient reference value of the free energy or whatever energy we're looking at. And we're looking at changes with respect to that reference value. The free energies also come with different names. Gibbs energy, Gibbs function, free enthalpy, and the Helmholtz free energy is also called Helmholtz energy or Helmholtz function. And now there is something I'd like to say about these pictures. Okay, taking pictures in the 19th century probably wasn't a picnic. In particular here, Hermann von Helmholtz, he really looks like he has better things to do. But that said, that was just a joke. These people were geniuses. And if you read about their achievements, their lives, it really impresses you. Well, it impresses me how brilliant these people were and the things they could come up with even in the 19th century. And for that reason, it's just nice to learn about the history, read a little bit about these people, what they have done, and how their private lives look like, for that matter. Now, let's go back to the Gibbs energy for a minute and have a look at it in the context of chemical processes. Chemical processes or reactions, they can be either exothermic or endothermic. And maybe you remember from your high school chemistry that exothermic reactions, they occur spontaneously and they are accompanied by a change in enthalpy that's smaller than 0. And endothermic reactions, on the other hand, they require heat to be added from the environment into the system in order for the reaction to take place, and they're characterized by a change in enthalpy that is larger than 0. So the enthalpy change seems to be kind of a predictor of whether a process can take place spontaneously or not. And this is a bit confusing because we had defined the concept of entropy as an indicator of spontaneous processes. And we know that they can be spontaneous if the entropy increases. So these two concepts seem to be at least competing. And the question is how to reconcile these two different concepts. Well, the answer is the Gibbs free energy. That exactly gives you the relation between changes in the enthalpy and changes in the entropy. And that's why the Gibbs energy, and for similar reasons also the Helmholtz energy, are very nice indicators of whether the process can take place spontaneously or not. For example, the Gibbs energy can help us answer the following question. Assuming that we have a system of which we know the temperature, the pressure, the composition, so basically we know the thermodynamic state of that system, how to establish if the system is in chemical equilibrium. And for example, we could be looking at some sort of reaction chamber. It's a closed system. We make sure that the pressure and the temperature remain constant, and it's at an elevated temperature such that this combustion of carbon monoxide can take place. So you oxidize carbon monoxide to form carbon dioxide, But because of the elevated temperature, these carbon dioxide molecules can also be dissociated, and they break apart in the original molecules again. And these molecules is what we are calling reactants, and these molecules is what we will call products. Now let's try to look at this, try to answer this question with the help of thermodynamics. Well, we have the first law of thermodynamics, which is energy conservation, which for a closed system reads as follows. And we have the second law of thermodynamics, which comes in different incarnations. One way is sort of a verbal way, saying that the entropy S always increases until equilibrium is achieved, and thereby a maximum value of S. But you can also phrase it in terms of the Clausius inequality. And I'm writing this here because we will use it later on the next slide. And so this reaction, suppose we're starting from purely carbon monoxide and oxygen, then they will start to react. And as the reaction takes place, the disorder in the system, in this chamber, will increase. So thereby the entropy will increase. But assume that everything would be converted into carbon dioxide. We would only have carbon dioxide molecules left. Then actually the disorder would be smaller again. So the entropy would be smaller. So this is a bit, well, this is not the final state that we're going to achieve, because somewhere in the middle, while this reaction takes place, the entropy will increase until it reaches a certain value that's higher than the value over here, and the reaction will stop. This is when equilibrium will take place, and that means that the reaction in this direction, from left to right, is taking place at the same rate as the reaction going from right to left. Now let's see what we can do with the help of the Gibbs energy here. So we saw this expression, which we find from the first law of thermodynamics. This is again the Clausius inequality, and combining these gives us this inequality here. This entire thing is smaller or equal to 0. Let's take a look at the Gibbs function, which is the enthalpy, U plus P times V, minus Ts. And this is, of course, evaluated for constant temperature and pressure. And then, well, you may take some time to read through this, but you find that the total differential of the Gibbs energy is equal to this expression here, which is exactly equal to this one. So we find that the differential dG should always be 0, or should always be less than 0. And what actually is happening while a chemical reaction takes place, the Gibbs free energy will be decreasing and decreasing until it reaches a maximum where this dG becomes 0, and that's it. That's when equilibrium is achieved, and you will not go up this curve again, because you would be violating the second law of thermodynamics. Okay, so we saw 4 different thermodynamic energies: internal energy, enthalpy, and now also Helmholtz energy and Gibbs energy. These are the expressions that we came across. Each energy has its associated total differential. We saw these special partial derivatives, which are basically, together with this expression here, are an embodiment of the state postulate. And we saw why these things are called fundamental thermodynamic relations. And of course, all these 4 thermodynamic energies are state functions. They are exact or total differentials, and they can be regarded as equations of state, which are very fundamental. So in conclusion, 4 thermodynamic energies. We saw that on the previous slide. There are also the state variables, temperature, pressure, volume, and entropy. So in total, we have 8 properties of which we have been taking partial derivatives, all sort of sorts of partial derivatives. Actually, how many partial derivatives can we make given these 8 properties? Well, in fact, we can make 8 to the third different partial derivatives, and this power of 3, or this exponent of 3, follows from the fact that each partial derivative contains 3 different or 3 variables. So we have 512 partial derivatives that we can try to compute. And then in addition to that, we have the path functions, the non-exact differentials, things derived from work, heat, and entropy generation. So, okay, there are 512 partial derivatives that we can form. And of course, we want to be able to find all of them. Now, some of them are trivial. Dx is 1, of course, and dx dy is 0 if you keep x constant. Some of them we have already evaluated before, so we know them. Some others are easy to evaluate if you know the equation of state. For example, for an ideal gas law, this is easily found. But what about the roughly 500 others partial derivatives? How do we obtain these? And in particular, the ones involving entropy, because that's notoriously difficult to measure. Now, that's what we will learn about in class 16b. We will learn about nice tricks to convert partial derivatives in terms of not so handy variables into expressions that involve easily measured variables. And we will see another few interesting things. Now here's the slide with the important formulas. If I would add all the things we saw today, if I would add that to this slide, it definitely wouldn't fit anymore. But again, try to keep these equations in mind. Many thanks to Geni again for letting us use her slides and also occasionally explaining us a thing or two about thermodynamics. And then finally, there's a slide that we have seen also in the previous classes. Let's try and see if we can store things in your long-term memory. So take a minute, maybe literally 60 seconds, to look back at this lecture and decide for yourself what was the main topic of this class and which aspects were the key elements. And last but not least, always feel free to approach us with comments and suggestions and whatnot. Okay, see you online.